So thank you for coming. My name's David, and as we said, I'll be presenting an introduction to TensorFlow, and we'll have an example or two in Python. So we're going to be, first of all, looking at what TensorFlow actually is, what it does for us, and we'll cover some of the terminology and the concepts. And then we'll look at some examples of it being used in the wild. And then from there, we're going to dig into one of the examples, see how we can get started. And again, we'll be covering some more of the concepts and terminology. And then hopefully that'll put you in a position where you can kind of pack your own parachute and launch yourself into your next project with TensorFlow. And as we mentioned, hopefully we'll have a few minutes for questions at the end. If we don't get a chance to speak, my contact details will be up on the last slide, so please feel free to drop me a line or grab me at the conference. So, TensorFlow, what is it? Well, it's a framework. It's a set of libraries, services, interfaces, and they're there to take away some of the complexity and the pain associated with the process of defining, training, evaluating, and ultimately deploying machine learning models. And it abstracts a lot of that away behind some kind of standardized APIs, if you like, and various class structures. And as we'll see, it also helps to ease the process of exploiting distributed computing resources and also some kind of specialized computing resources as well. So we'll start at the top. These are the highest level APIs that TensorFlow provides. These are estimators, and handily Google have provided some pre-made estimators, which are really just pre-configured models that are designed to work on a specific task. Examples might be a recommender system based on reviews, could be films, could be products, image and object recognition. There are lots of others. There's a very rich library of models available. And the idea is that you plug in your data and apply the model to your problem. And we can, of course, build our own estimators. And the APIs at this level are there to kind of simplify that implementation. And effectively, you achieve a lot through configuration rather than any real kind of hardcore coding. Oops, gone too far. So alongside the estimators, we've got the Charis Models, and Charis, for those of you who don't know, is another open source library of machine learning models. It's pretty diverse. It's renowned for being very easy to work with, and there are some really quite sophisticated models in there. So you may be wondering, okay, well, why Charis and not estimators and vice versa? And it's not really a binary decision. You've got two really good kind of complementary frameworks. Charis can run on TensorFlow. Charis Models can run on TensorFlow along with other systems as well, or other frameworks as well. And TensorFlow really takes care of a lot of the, as we mentioned, the management of distributed computing resources and the coordination and some of the complexity associated there. And Charis, as we said, is a very rich library. And so support has been directly built into TensorFlow for Charis models. And there's a single line of code there that you can use to convert a Charis model into an estimator. And that brings with it a certain number of benefits in terms of scalability and portability that we'll come to in a moment. So moving down a layer, we've got a couple of abstractions. We have data sets and layers. Data sets really there to help with the process of loading data, unsurprisingly. We can work with different data sources. We can load them into different data structures, NumPy, pandas, amongst others. And then we've got the layers data structure, which is really there to help us group different parts of our model together, parts of the model that are going to work in unison to achieve a given goal in the context of the overall model. And we can add and remove them as we need. And then as we drop to the lowest level, we've got access to all of the fundamental components of TensorFlow. In this particular case, Python is the weapon of choice, but it's not the only client language available. And at this level, we've got access to graphs. It's a fundamental component in TensorFlow. It's an execution dependency chain, and it maps the operations that need to be performed in the correct order to achieve a given outcome. Now, those operations could be as simple as basic arithmetic through to full implementations of a machine learning model. And then we've got placeholders and variables. If you've ever worked with a database before, the placeholders are very similar to bind variables. And then variables, a specific term in TensorFlow, or a term that has specific significance. You'll often see these used for the parameters of the model. These are things that are going to be modified during the training process to help improve the predictions that a model is able to make, and we'll come to that a little bit later. And there are lots of other terms, but we'll come to them as we need to. And then underpinning these libraries, we've got the execution engine. And really that's able to take our graph, our execution graph, and it can distribute it across remote computing resources, server farms, so on and so forth, or run it on your laptop, your desktop PC. And it takes care of a lot of the scheduling, restarting, a lot of the complexities associated with distributed computing coordination. And we've also got an abstraction layer between the libraries and the specialized computing units, GPUs, TPUs. So it really is possible to justify this kind of setup for research purposes, of course. And then one powerful aspect of the TensorFlow architecture is that we can train, test, and deploy our models on anything from a Raspberry Pi through to an in-house server farm, your laptop. We can ship it out to numerous cloud providers. And if we use estimators as the basis for our models, we can do all of that without needing to specifically code support. It comes kind of out of the box support for that. And also with GPUs, TPUs, and so on, we get the same kind of support out of the box. And we can, of course, make use of these resources without using estimators, but we have to do a lot more of the plumbing ourselves. And in the case of TPUs, there's additional coding that we need to take care of ourselves to make sure that we can exploit those particular resources. So hopefully that gives a little bit more background on a high-level overview of what TensorFlow actually is. So we should probably move on to look at how it's been used in the wild. So the first example we're going to look at is AlphaGo. And for anyone that's not aware, it's a project that attempted to build a machine learning system capable of playing the ancient game of Go. Now Go has got some very simple rules. You can place your piece anywhere on the board, but if I surround it with my pieces, I capture it, and I've also captured that territory. And then the game's over when we either lose the will to live or we actually can't play any more moves. And then we count up whoever's got the most pieces and the most territory, and whoever has the most wins. Now, many people believe that Go would never be solved by a computer, or if it was going to be, it would at least be several decades away. And I think to give some context about how difficult Go is as a problem to solve for a computer, I thought it was worth looking at the total number of moves or total number of games that can be played with some well-known board games. So if we look at noughts and crosses, tic-tac-toe, we've got around 250,000 different games that we could play. Connect 4, we're up to about 4.5 trillion. Once we get to chess, there is a lower bound of 10 to the 120. Go, a lower bound of 10 to the 172. So there's a 52 order of magnitude difference between chess and Go. And those numbers are pretty meaningless to me. I can't visualize or conceptualize them really. So I thought it'd be fun to see if I could find an example that would illustrate that scale of difference. And the best I could do was to say that if all of the games of chess that were possible were represented by a single molecule of water, even if we took all of the molecules of water present on Earth, we would still be 9 orders of magnitude short. So we would need all of the molecules of water on 1 billion more Earths to represent the difference in the scale of problem between chess and Go, which is quite a lot of water. And you might be asking, okay, well, why am I laboring this point? Well, there was a gentleman called Claude Shannon, who in the 1950s, he concluded that because these numbers are so enormous, that taking any sort of brute force approach to the game of chess, any sort of exhaustive search approach to generating moves in chess just couldn't possibly work. And by extension, that's even more applicable to the game of Go. So to solve the problem, you have to take quite a different approach. And that's what the AlphaGo team did. Now, human players talk about developing an instinct for which moves to play and which strategies to employ. And so the AlphaGo team tried to distill that into a model by taking all of the moves from thousands of games and training a series of neural nets and various machine learning algorithms so they could arrive at a system that could even play the game of Go. And the process took several months, but the net result was that they were able to train a system that was able to beat a gentleman called Lee Sedol, who's one of the most highly ranked Go players in the world. And it beat him by 4 games to 1. Not only did it beat him, it was able to do so by using strategies that had never been seen before. It used techniques that kind of went completely against the perceived wisdom of the Go community. And to celebrate that amazing feat, the DeepMind team decided to throw it in the bin and start again from scratch. And this time they developed a model that just had the rules of the game encoded. So no observation of human players. And then through several million rounds of self-play, in just 3 days, AlphaGo was able to beat AlphaGo Zero, was able to beat AlphaGo by 100 games to 0. And it's been adapted to chess and Shinzo, and it's done very well in those areas as well. And at the end of the presentation, I provide a link to a repository where you can build your own version of AlphaGo Zero, but for Connect 4. So all of that's very interesting, but it's not necessarily reflective of the types of problems, certainly that I have to solve on a daily basis. So the next example starts with quite an intriguing quote that I saw from an embedded systems engineer called Makoto Koyoki. And he said, "When I saw Google's AlphaGo, I realized something serious is happening here. And that was the trigger for me to start developing the cucumber sorter with deep learning technology." And I think this is a really good example because it highlights some of the key features of TensorFlow and also some of the problems that we encounter when we're building machine learning models. And as with most good projects, this one started with a problem. So Makoto's family own a cucumber farm in rural Japan, and they grow cucumbers that are sold to a variety of different suppliers. And they're hand-sorted, and the best ones go for the highest prices with the supermarkets and so on, and the worst ones go for a fraction of the cost at the local markets. Now, the process of categorizing takes months to learn, so it doesn't particularly scale well around harvest time. Temporary workers can't be trained particularly quickly. And while there is existing automation in this area, it's expensive, it's not particularly flexible, and it's quite bulky. So Makoto wondered if there was a cheap way to categorize the cucumbers on the basis of image analysis. And he started to look at TensorFlow. And one of the first examples that you come to when you look at the TensorFlow library is a handwriting recognition model. And after looking at this model, Makoto realized that the process of classifying images of cucumbers wasn't actually a million miles away from classifying handwritten digits. So on the left, we've got handwritten digits, and on the right, we've got the pictures of cucumbers. And we've got 9 categories of cucumbers instead of 10 categories of digit. But other than that, there isn't really a great deal of difference between the individual images. So Makoto took the project and he adapted it to his problem. And so we'll just have a quick look at what he achieved, and then we'll dig into this particular example. So he exhibited at a maker fair, showed off what he'd built. He built quite an impressive installation in his farm, and there's a video of this if you're so inclined on YouTube. TensorFlow cucumber is quite a specific search term. Should get you to the particular video. So all of this was done on a desktop PC. The training process took several days through a process of trial and error, changing various parameters and configurations. He was able to get 95% accuracy during training. However, that dropped to about 70% during testing. And it highlights quite a significant problem that we come across with machine learning models, overfitting. The model learned the features of the training data too closely. It couldn't generalize. So, it perhaps learned that, a top-notch cucumber should have been 27.2 centimeters instead of saying anything over 26 centimeters is fine. And I've made that up, by the way. I don't know whether that's true or not. And so he started to work on prototype 2 and throw more data at the problem. So increase the resolution of the images, use full color, multiple photos from different angles. He took a lot of photos of cucumbers, 7,000 training images and another 1,500 testing images. And after that, he managed to improve the accuracy to around 80%, which is good, but still not quite where he'd like it. And then prototype 3, Google picked this up on one of their blogs, and they suggested an architecture that he could use to integrate with their cloud. And the tagline for TensorFlow is an open source machine learning framework for everyone. And I think Makoto's example shows just how accessible and versatile the framework can be. The barrier to entry is low. There are no licenses to buy. Minimal hardware requirements, excellent community support. It's pretty portable, Mac, Linux, Windows, and there are projects underway to make it available on mobile devices. And I think the talk after this one highlights the JavaScript implementation. And I think there's quite an interesting point about scalability here, that we often look at scalability as about more how many more CPUs can we throw at the problem? How many more servers can we throw at the problem? But actually, with Raspberry Pis, mobile phones, edge devices, it can quite often be about scaling the problem to the hardware that's available. And in this case, for example, Google suggested offloading the basic image recognition, is this a cucumber, or is it the operator's hand, to a Raspberry Pi, and then doing the more intensive workloads, such as categorizing the cucumber and training the model even in the cloud. And then the final point really is around simplicity versus difficulty. As we'll see, that it's not difficult to build complex models. So now we'll have a dig into some of this code. So this is the code listing, the full code listing. It uses the Modified National Institute of Standards and Technology database. So there's around 70,000 examples of handwritten digits. They've all been scanned, reformatted to the same size and shape and so on. And they've all been labeled. And I've highlighted in this text 9 function calls. And we don't really need to worry about what they do right now, but that's 9 function calls to train, test, and evaluate the performance of a handwriting recognition model, which I think is quite impressive. And yes, there is a little bit of cheating going on. This particular call up here, this wrapper function, the MNIST dataset has already been packaged up and provided with this particular distribution, and the training data has been split and so on. But it's not hundreds of lines of code. It's literally a couple of tens of lines of code, and it's quite simple, straightforward stuff. The meat and bones is really the definition of the model. And interestingly, 5 of those function calls are defining the topology of the network. So the first line of code, I'm not going to go into the mechanics of how we load data into Python data structures and so on. Instead, we're going to have a look at what data this function provides and the format of it. So the data set's been split into 60,000 training images and 10,000 testing images, and it's further split into X and Y arrays, X representing the features, the data that we want to attempt to classify, and Y are the labels for that data. What is this digit representing? And then if we look more closely at one example, we can see that it's a 2-dimensional array, 28 by 28, and it contains integers in the range of 0 to 255, and they are the intensity levels on a grayscale. And to support the calculations that we do in the model, we need to rescale those integers to floating points in the range of 0 to 1, and that's what the second line of code does. And we'll see why that's important in a moment. So basically, the data has been prepared and processed, and we're now ready to start building the model. And that's what this chunk of code here does. Now, there's a lot of detail about the various different network topologies and so on, and that's quite way outside the scope of this talk. So what we'll do is start having a look at the structure of this particular model and relating it back to the individual lines of code. So starting with the first call, sequential, right up at the top, that just refers to the way that we're going to build the model. We're going to add layers sequentially, and they'll be processed sequentially. And then each subsequent call adds a new layer to the model. So the flatten call is a transformation, and it converts that 2-dimensional array into a vector that has 784 elements or features. And this is our input layer. And then the next 2 layers are referred to as our hidden layers, and that just means that they're not exposed to the outside world. And then the first of our hidden layers, dense 512, that creates 512 neurons that are connected to every feature in the input layer. Bit of basic multiplication, 512 neurons times 784 features gives us 400,000 odd connections, and that number will come back to haunt us in a minute. And then the second layer, the dropout layer, and we touched briefly on overfitting, and the dropout layer is basically taking quite a simple approach to dealing with the problem of overfitting. During training, it's going to select a number of neurons at random to effectively drop from the process, and the idea is that by doing so we can eliminate reliance on some specific features that may be causing some of the overfitting, and the 0.2 just refers to the percentage, so 20% of the neurons are going to be dropped. And then finally we've got the output layer. It's another dense layer, this time with 10 neurons, one for each output class. We don't specify which classes each one relates to. That's figured out as part of the training. And so we've talked about the neurons, but we've not actually looked at what happens inside one. We've got a couple of extra parameters in those two dense layers that were created for us. And the calculations that happen inside the neuron are actually quite straightforward. We have the input data, our features, and then we have a weight parameter for each neuron for each feature. So that gives us our 400,000 or so weights across our entire model. And then there's a final parameter for each neuron, which is the bias. So we multiply each feature by its assigned weight, we add the bias, and then we sum them all up, and then we pass them to an activation function. And that really just determines whether it's worth this this neuron producing an output and what output it's going to produce. And the two activation functions that we see in here are ReLU, rectified linear unit. It's just basically a posh way of saying whichever's greater, 0 or the result of our calculation. And then we've got softmax, and that returns a vector containing numbers in the range of 0 to 1. They all add up to 1, so we can kind of treat them as probabilities. And in this case, it's the probability that any given prediction belongs to a given class. Nothing's ever 100%, or very few things are. So in this case, it might be that there's a 0.55 chance that this is a 4, and it's a 0.2 that it's a 3, so on and so forth. So then we need to jump forward a little bit in the code. We're going to skip over this line just briefly, because some of the stuff that we'll cover in the training process will then give us a bit of context to what these particular statements mean. And as we saw, each neuron has an associated weight with each feature. And these are termed the parameters of the model, and they're adjusted during training. As we said, there's a lot of them. And the weights have to be set initially. Now, we could set them all to 1s, we could set them all to 0s, we could arbitrarily pick a number to set them to. But as with many things in machine learning, adding a bit of randomness can be highly beneficial. Now, all of this is taken care of for us behind the scenes. We don't need to worry about doing any of this, but I think it's worth understanding a little bit of what's going on behind those lines of code. So then we jump forward into the training and evaluation, the fit and the evaluate process. So the training process, it takes an example and it propagates it forward through the network, through each layer, and it arrives at a prediction. It uses those initial random weights to perform all of the calculations in each neuron and so on. And then after a certain number of examples have been processed, it evaluates a loss function, and that calculates how well the network has performed in its prediction. And it does this for each neuron in the output layer. And then with that understanding of how well the prediction has been made, it attempts to figure out how to distribute that across the the neurons in the network. Effectively, it figures out how to point the finger at the neurons that are doing the bad job. And then the final step is an optimization. It attempts to update the weights in a way that helps to minimize the loss function. So it's not updating them at random, it's trying to do them in a measured way. And as it's doing that, it has to be, we have to be careful that we don't encounter more problems. So if we update the weights by too much, we run the risk of overshooting that minimum. If we do it by too little, we run the risk of never completing, or at least taking a very long time to complete our training. And in each case, we're calculating, calculating a gradient, how much to update this particular weight by. And then the final part of the training process that we're going to look at is the Epochs argument. Implicitly, the fit function is going to split the data into batches. The default is 32 samples per batch. So that's going to result in 1,875 batches, given our 60,000 samples. And again, by default, those batches are going to be shuffled. They're going to be selected at random. And for each batch processed through the model, it's going to perform that back propagation exercise, so it's going to update the weights and the biases. And an epoch refers to the number of times the training algorithm is going to iterate over all of the examples of data. In this case, it's 5. So it's going to process all of the examples 5 times, and it's going to do it in 9,375 batches that are all randomized. And equally, it's going to perform the back propagation exercise that same number of times. And then finally, the evaluate call. And that's going to run our 10,000 test samples and produce some metrics about the performance of the network. So now we've gone through that process, it's time to jump back to that line of code that we skipped over. And so hopefully some of these terms will perhaps be a little clearer. So we're defining the optimizer, we're defining the loss function, and we're specifying how we're going to measure the performance of the network as a whole. So the Adam optimizer is one of several available. And it's particularly good because it's able to adapt the learning rate, i.e. the size of the jump, the gradient, to the individual weights within the individual neurons. So it can treat them with a bit more nuance. Gradient descent, stochastic gradient descent, you may also be familiar with, tends to use a more uniform learning rate. So Adam tends to work a little better in a lot of cases. And then the loss function, in our case, we're producing a series of probabilities for each class, and cross entropy is a measure of how accurate our predictions are across those classes and how distinct they are from each other. It uses a logarithmic scale, so it actively penalizes the predictions that are furthest from the truth or least clear. And the worse the prediction, the quicker the model can learn. And then the metrics, if this was a regression problem, if we were predicting house prices or something like this, there are lots of different measures that we could use as its classification. Accuracy is quite appropriate. We can also specify our own using things like callback functions and so on. And so that's the example in a nutshell. And really, it's then a matter of saying, how do you get to grips with it? What do you take as your next steps on the journey? So the example that we reviewed, it used a Charis model for handwriting recognition. There are a few other variations on this theme. It uses different network topologies, convolutional neural networks, for example. So it means that you can test them against each other. You can assess the performance of one model versus another quite easily. And then from there, Charis has got quite an extensive library of examples covering other forms of image classification, sentiment analysis. You can classify news articles by topic, text and label generation, and they're all supported by really good data sets. And there is some pretty cutting edge stuff there as well. And then TensorFlow also provides some good pre-built models on everything from visual navigation through to the snappily titled contextual bandit algorithms using deep neural networks and Thompson sampling, which I think is pretty self-explanatory. And then finally, the AlphaGo 0 implementation that we saw at the beginning for Connect 4. Now, this is obviously a fair bit more advanced and more complex, but I think it illustrates some really interesting concepts and how multiple machine learning models can be combined to achieve a single goal. And I think between those three resources, there's a really good range of models and problems to investigate. And so to recap, we had a look at how flexible and portable TensorFlow is, and how low the barrier to entry can be. We had a brief look at AlphaGo and the seemingly impossible task of teaching a computer to play Go. We looked at a far more human scale problem and how a cucumber farmer in rural Japan has repurposed a handwriting recognition tutorial to solve a real productivity problem. And then finally, we had a look at some of the code to see what it was doing behind the scenes, and just how little work we actually have to do. And we covered some of the concepts as well. So I hope you found it useful, and I'd be happy to take any questions.